Today, Science Max is all about sound. We bend the power of sound to our will by making the loudest sound we can.
Wait a minute, a subwoofer.
Subwoofer.
Make cornstarch mud dance, glasses break, and things vibrate. It's the sounds of science. Today on Science Max, Experiments at Large.
Greetings, Science Maximites, and welcome to... Can you hear me? Greetings, Science Max! You can't... hold on a second.
Greetings, Science... Yeah, that's much better. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. Today, we're going to be talking about sound. Sound is all around us. We use it every day, but what is it really? Sound is energy. Let's say that this is the... No, stay. Stay. Okay. That this spring is the sound of my voice. When I make noise, it travels away from me in a wave. One air molecule vibrates the next air molecule, vibrates the next, and it looks like a wave. And when there's a little bit of energy, the wave doesn't move very much. Science. But when there's a lot of energy, the wave moves a lot. Science! What do we do? What do we do to make sound louder? This is the Science Max theme song. But it's not very loud because the speaker on my phone isn't designed to make super loud noises. So what we're going to do is find ways to make the volume of that song as loud as possible. Here is one way. Take a phone playing some music and put it in a glass. Make sure the glass is empty, of course. Huh? And suddenly, it's a lot louder. Wow! Why this works is one of the things we're going to be looking at today. So that's what we're going to do today on Science Max Experiments at Large. We're going to learn how to make sound louder, as loud as we can. But I'm going to need an expert to help me. Oh, I know, Michaela from the Ontario Science Centre. She's very smart. All you need to do is go to the Ontario Science Centre and see if she's busy. Yeah, Michaela, it's good to see you.
Nice to see you too.
That was weird. I was wondering if you could give me a hand with an experiment.
Oh, I'd love to, yeah.
It's a sound experiment.
Sounds awesome.
Right on. Okay, we'll take the portal. We'll go back to Science Max headquarters.
Oh, we can take the portal? Cool.
Haven't you taken the portal before?
No, don't you remember? It wasn't working last time.
Oh, well, it's
Is it working?
fixed this time. Yeah, no, it'll be great. Trust me. Here we go.
Whoa. What's going on, Phil? Is everything okay?
Usually when I come through the portal, I land on something or something falls on me or...
Not today. It's your lucky day.
I guess so.
Safe landing.
Safe landing.
Nice.
High five. All right, so let's get started.
Okay, cool.
This is the experiment I want to max out today, Michaela. I know. Pretty impressive, right? No, hold on.
Okay.
So I take my phone and I play some music on my phone and it's louder, right?
Check it out. Phil, you've just made yourself a resonance chamber.
A resonance chamber.
A
Very
resonance
nice.
chamber is what we say when we're trying to describe how the sound is amplified. So if the sound's coming in from one direction, it's bouncing around, not really losing energy. So when more sound comes in, that's amplified. We hear it a lot louder.
That's cool. So that's what I want to do. Hold on, let me turn this up. That's what I want to do today. I want to max out as much sound as we can get out of the Science Max theme song, which
I'm
is
so excited.
totally awesome. So what else can we do to do that?
Well, there's a couple avenues I'm thinking. Do you want to try something with electricity or without electricity?
That's because with electricity, we're talking speaker systems and
Yeah.
Right. So
We
why
can
don't we
get into
do no electricity for now, and then
All
we
right.
can jump to electricity when we feel we've exhausted everything that's non-electric.
Cool. So I was thinking we could try to make a megaphone, because if we have a lot of sound, we could, funnel it in one direction, and then it would be louder.
Okay.
What do
Yeah.
you
So
think?
the megaphone's pretty easy to make, right? We could just use. In fact, we could use this piece of paper, right?
Yeah, let's try it. What do you think?
I think it's very megaphony. Science taping it up. Okay, ready? Okay, turn it on. play it. And doesn't sound, but what if I do this?
Hey, there it is. Right on.
Oh,
That song.
yeah? You hear it?
Yeah. Oh, I hear it.
Okay. So that worked pretty well. So.
Oh, yeah, it works. Works, Phil.
So this is pretty easy, right?
Yeah.
Megaphone?
Oh, yeah.
So why don't we max this out? Why don't we make a giant megaphone and see if it makes a big difference?
I think it will. Let's do it.
Sounds good. Let's get started. All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic, like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt. The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance. But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look. The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes. So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. Whoa. So Michaela and I are on a quest to make the loudest sound we can. The first step is to make things louder without using electricity. We've looked at a resonance chamber, and now we're going to make a large megaphone. Sounds can be amplified by bouncing sound waves around in a space. When I put my phone into the glass acts as a resonance chamber. The sound waves bounce around inside the glass, and they combine and stack on top of each other. This makes the sound louder. Resonance chambers are used by musical instruments like an acoustic guitar. The wooden chamber bounces the sound waves around, and the sound waves build on each other to make the sound louder. A megaphone bounces sound waves as well. Instead of going off in all directions, a megaphone makes the sound waves all go in one direction. That's one of the reasons why a megaphone makes sounds louder, but only when it's pointed at you. So will a bigger megaphone work better? So we've made a larger megaphone, which is exactly the same thing. You just take a sheet and you roll it up, except our sheet was plexiglass covered in paper, and we've taped it together so it stays. And the idea here...
Oh yeah, bigger megaphone. We're gonna vibrate even more of the air inside of here, and hopefully this thing will be louder.
Okay, so you're ready to try it with the phone?
Yeah.
I think first we should try it with our voices, though.
Okay.
Phil, what's your favorite season?
Awesome, I can totally hear you. That's amazing. And it would be fall. No, summer. Spring?
Think
It's
about it.
anything but winter. So the maxed out megaphone worked, but we still had to try it with my phone. Okay.
Not bad.
Yeah?
Oh yeah. Oh, definitely.
How about now?
No, not so much. Not so much. Oh yeah. Nope. Nope.
So that is a
That was
great
cool.
example of non-electrical amplification.
That's right.
Amplified the sounds, no electricity. Okay, high five. All right. Come on, make some noise! Well, to know that, you gotta know your sound. All sound is vibration. Here, take a closer look. You see? You got... Okay, let's try this again. All sound is vibration. The string of this guitar vibrates, which vibrates the air around it, causing the sound that you hear. Your vocal cords vibrate in your throat, causing you to make a sound. Ah, 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 la, 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 la. Look at this thing. Look at this thing. See how it's shaking back and forth? It's vibrating. Things that make a high sound, they vibrate faster. Vibrating really fast. Things that make a low sound, vibrate slowly. High note, vibrating fast. Fast! Fast vibrating! And now you know your sound.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big. The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here. This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger, and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud? And yes, this is something you should not try at home. This note makes the glass vibrate the most. Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks. The vibrations were so strong that the glass literally shook itself to pieces. Science! Sorry. Science! Oh, wait. Science! Michaela and I have tried a resonance chamber and a giant megaphone to make sound louder. Now it's time to move on to the next step of the plan, using electricity to help us amplify sound. And that means speakers! So, speakers that you have at home, 3 different speakers here, right?
Looks
3 different
really busy.
cones.
Yeah, there's a lot going on.
So, what's the deal?
Well, here at the bottom, we have a subwoofer.
Wait a minute, a subwoofer.
Subwoofer.
So it's a woofer, the word is woofer?
Yep.
And it's, okay, so it's for dogs, right?
No, a subwoofer is for low notes here in our speaker.
Ah.
At the top here, we have a tweeter.
So it's for birds. It's it birds, dogs. So low, let me guess, low notes?
Yeah.
Tweeters, high notes?
Yeah, high notes. And then we have this guy here in the middle, and that's called your mid-range speaker.
Oh, that's not nearly a cool name. Now we have speakers, we've taken a look at that, but why don't we take one apart,
Cool.
right?
Yeah, let's do it.
I've got this one here that I spilled juice on, so it doesn't work anymore. So I've kind of taken it apart. So
Cool.
it's got
Oh, man, that's awesome.
Okay, so it's got the cover. That's cool. So what I find interesting is there's the speaker and the wires, right? Because it's electrical amplification. But check this out. This is just a ring to hold that on. And the rest is just an empty box.
We know what that is. Resonance
chamber. That's right. So that's why it's an empty box. So
Let's take this apart too, see what's going on.
So that's the paper cone, right? So that's the drum, I guess. It's like the eardrum, the thing that vibrates.
Yes, yeah, this whole thing vibrates.
So this whole thing.
That's for electromagnet. When we turn this on, the electromagnet goes on and off, and it's causing this whole thing to vibrate.
So that's how it works. It's the electricity turning the electromagnet on and off.
Exactly.
And it's on and off and on and off and on and off and on and off. And then it makes it vibrate at certain speeds, right? Hertz. The number of times it vibrates per second is hertz. What we could do is we could max it out with the speaker and plug the phone into speaker. But this step does not feel like Science Max to me because anybody can do that, right?
Yeah.
You can just turn up your television right now, and that's pretty much the same kind of thing. We need electrical amplification, but maxed out.
Max it up. What are you thinking?
Okay, so I've got a friend, and he's got a stereo system that he built, he put together, and what he does is he tours different cities. So he said he'd bring it by Science Max headquarters.
He's gonna bring it here?
We gotta go outside.
We can see this thing.
And it's very loud, so we have to go outside.
When's he coming?
Right now. All right, let's go check it out.
Seeing sound vibrations is fun.
This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds.
I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then, tape it so it's nice and secure.
Then, what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water.
I've got some yellow cornstarch and some blue cornstarch.
This experiment works the best with low notes.
I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume.
It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. Science!
So Michaela and I are going to max out sound. To do that, we need a maxed out sound system. Isn't it amazing? This is gonna be super maxed out sound experiment. This is
so
James,
pumped.
Michaela.
Hey, James, how are you?
Thanks for coming, buddy. Nice to meet you. So, tell us about your speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Wow.
So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that better when you have a van like this?
With a car audio van like this, you want to play low notes, like your house stereos, and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of
Yes,
thunder,
very
kind
low.
of blah, 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 blah,
Yeah.
where you really feel it,
Yes.
like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much.
I'm totally jealous of your long hair.
Yeah, you need to get longer hair.
Okay, hold on. I'll go right.
Okay.
Whoa! Science Mac! Experiments at large! Super sound! High fives. Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
At the bottom.
I can't reach it. So that's great. Wait, almost. No, I can't. Okay, I got my hair protection on. You got your hair protection on?
What was that?
Hello? Oh, hi, Mom. No, I'm shooting the show right now. I can't. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing. Ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Centre. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out.
And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather. How you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh,
we'll
via the portal?
Yeah, by the portal.
Okay.
You sure?
I
I know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay. Don't worry about it.
No,
No,
I think
it's fine, it's
definitely.
fine, it's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery,
Yes.
more voltage, and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century, but no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. and wrapping, and wrapping. There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out, because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity. Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger. Okay, so we're gonna try this electromagnet and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, we
Not
turn
bad.
it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe
Oh.
we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need. A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers. So here's what you do. First thing is you put the batteries and the magnets together like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here. And if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger, and of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement. Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets. What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great.
We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery.
Do you think 12 volts will be enough?
Let's find out. I think so.
Try that.
Once we do, it works much better.
Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's,
Here.
I can't pull that off. Okay, wait, grab this. Okay,
Work together.
yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is
What
there
do
a way
we...
to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms.
Want to turn it on?
We're ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until...
Oh, okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on.
This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo, and prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end?
Not really, no.
But would you be impressed if I was to balance this coin on top of this coin?
Possibly.
Prepare to be flustered and stupefied. Stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this. And now I say a magic word. A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing! Oh!
Is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No! This is set dressing. It's just for...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks. Maybe 3 pairs of socks.
We can still see you.
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh. Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got...
2 electromagnets, 1, 2.
And those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because...
We need to keep you safe because you're gonna be using these electromagnets to get across this massive beam above us.
That's right. I'm gonna stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
Oh my goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets! Woo! You wanna go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Oh, careful. Don't mess it up, Overwhelmo.
Overwhelmo.
Send in the next applicant for the Wizard Academy.
Overwhelmo.
And now, I say the magic word.
Overwhelmo.
I say the magic word. The magic word!
Well, that certainly does seem like magic, yep.
As I balanced out 1 coin, not 2 coins. That's a 3.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is all about generating electricity.
Where do we get this electricity that we use all the time?
We try to generate as much as we can using human power, plus solar energy, tidal energy, wind energy, and more. All you need to do is
Turn the generator.
all on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. Attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape.
It's the same as invisible tape, except I use this one for science.
A cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because today, on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although, one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it. So I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So you think this is a good size?
I think this is great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
To red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and I'll turn the generator.
Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach to the end of the generator so we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect. Okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5.
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still, a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So
yeah.
Maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out. It goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. 1 on either side, and 1 on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works. Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand.
It is now a stationary bike. It'll be even more stationary once we screw it down.
And attaching the generator.
All right, the bike generator. Bike-erator, what should we call this thing?
Bike-nomator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get 1 revolution here means a whole bunch is spinning
Exactly.
there.
The more we get here, the more our generator spins, and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that.
So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill. It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't, we can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into it going for a long time, you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly.
And that'd be a really fast motion. Spin it really quick and get a very high number.
High spike, exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay,
All right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang on a sec. I got it.
And maybe we should attach the horn to the next thing too.
Turn it off!
So you want to generate some electricity, but what do you choose to generate that electricity? Hydro, nuclear, coal, solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are two plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons. Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside, turning the spindle gets harder the higher the gear. Anthony and I attach a spindle and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set. Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah. Something like really big. So what if we could get like really high, like up there? Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That
and then
would
the
work.
rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So, if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about hydroelectric? We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there and ta-da, you're creating electricity with the power of hydro. Ha 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 ha, I did it.
Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible.
Okay.
Okay.
Crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here. Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter here.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. He's still off by quite a bit.
Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas,
coal power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes.
Okay.
Give me,
You take the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
So this is a solar panel, and this is a train. You're generating electricity. You're in the way of my solar panel. Oh, no, it's spinning the other way. I forgot a step. I forgot a step. The water in the oceans doesn't stay still. The thing in the background, it totally threw me off. What was that? Okay. Where were we? We were...
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Try yours. Real? What makes airplanes, or basketballs, or people fly? It's air. As well as a bunch of other things that we learn when we try to make a giant paper airplane.
So that didn't work.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ho-ho! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide, and open it up. And here's the trickiest part. See how it's bent like that? You push it open like this, and this is called a pocket fold because you want to make a little pocket and push it up against there. Fold it flat like this. Fold this tip down over there like that. Then fold it around the back side. Then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings and ta-da, the Sky King paper airplane fold. Now, as Science Maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, Experiments at Large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. Uh-oh, that's never good.
Whoa,
Phil, I'm so sorry. You okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents How to Fly Your Paper Airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. Sorry, high pitch.
Great, great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah. Yeah? No. Yeah. Yeah is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Here we go.
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace science and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh, yeah, you're
And-
right. The ink doesn't go straight. It follows the wing
follows
down.
the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right, and
generating lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay.
Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out.
I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Okay, be very careful getting off it. Whoa! All right, let's fold it. Nose on that side. Okay.
Remember, we're folding the exact fold we did in the lab, only on a larger scale.
We have a tape malfunction down here.
But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
Okay. There.
Perfect.
Yeah. Giant paper airplane! Ha ha!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Yep. Maybe.
Like, I'll just.
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah.
Go for it.
Okay, here we go. Wow.
I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look, let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very, very floppy.
Very floppy. What if we supported the plane, like we put struts or something in it, like this stick? If we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like, so
like
foam?
Yeah,
Stuff?
and like hollow tubes.
Hollow tubes?
Hollow
Good.
tubes.
Good. So we'll put a whole bunch on there. We'll tape them on so that it doesn't flop around.
Yeah.
We'll try it again.
Yeah.
Yeah, I think we got something.
Okay, great. Let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
There. And then that.
Great, look at that. It's not even flopping around. It stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be, well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just...
Phil, there's a lot of stuff on here.
There.
But like it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, well, yeah, let's do it, let's do it. All right.
Okay. All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, yeah, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber.
Hey, Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah.
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up. And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour. All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour. Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly. Oh, woo! There you go, our Mark III model paper airplane. Now I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap. But we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose.
We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Whoa, okay, all right.
Phil, that was great!
All right!
This throw worked best, but I know what you're thinking. Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is
Largest paper airplane I've ever thrown! Woo! Hey, you guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large. Where were the stairs? Yeah. Oh, never mind, I found them.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Does that sound like music?
Sounds good.
Stop!
Yeah.
Yeah.
Yeah?
Yeah.
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 Word has lost all meaning.
Science!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Put on your helmets for this episode of Science Max. We try to build a human-sized cart powered by inertia, plus Newton's laws from a caveman to crockery. Inertia on Science Max, Experiments at Large.
Greetings, race fans and Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the drag racer. Huh? Pretty cool. It works like this. You pull the string and get the wheels going really fast, and then you let it go, and it just drives away on its own. The interesting thing is I don't have to push it, it goes by itself. It all has to do with Newton's first law of motion, which is an object at rest tends to stay at rest, and an object in motion tends to stay in motion. Yeah. Let's get building. Here is everything you need to build your very own dragster. You need some popsicle sticks, some straws, and some shish kebab skewers. I love these. You can get these at the grocery store. Let's see, some elastics, and of course you want wheels, and I just cut my wheels out of cardboard.
So here's a quick explanation of how to build your dragster. First, use anything round to trace 3 circles out on your piece of cardboard. Remember, you want 2 big and 1 small circle. Then, cut out your wheels.
Then it's time to make the frame of the dragster using popsicle sticks and elastics. Just put 2 popsicle sticks together, then wrap the elastic band around them to keep them together. First you build one side, then the other side. Then add some pieces across the middle to give it support. Remember not to put any popsicle sticks too near the ends because they'll get in the way of your wheels. Next, cut the straws into small pieces and use an elastic band to tie them to the ends of the popsicle sticks. Then it's just a matter of sticking the shish kebab skewer in a wheel, passing it through the straws, and sticking on the other wheel. Don't forget that the small wheel goes in the middle at the front. You can trim the skewers afterward by just breaking it off short.
If you want step-by-step directions on exactly how to do this, you can go to our website. It's all right there. Now the last part is wrap some string around the back axle so you can pull and the wheels will spin. Let's check it out and see how it works. Didn't work that well, did it? That's because we haven't added the secret ingredient.
Plasticine, the perfect secret ingredient for all of your dragster needs. And also sculpting, because that's what it's for.
Remember how I said an object at rest tends to stay at rest and an object in motion tends to stay in motion? Well, the heavier something is, the more force you need to change its direction. Either get it moving or make it stop. That is called inertia. It's the tendency for an object to resist a change in motion, either getting it going or making it stop. So, the heavier we make the wheels of our dragster, the more they will resist a change in motion. So what I've done is I've stretched out my plasticine, and then you roll the wheels of the dragster around in the plasticine, and this will make each wheel way heavier than just the cardboard by itself. And it will make it much better in terms of keeping the dragster going, because if the wheel has more weight, it will have more inertia. Now, I have to wrap the string around the back axle, just like that, and there we go. All right, let's try it out. All right, let's give it a shot and see how it works. Pull on the string, get the wheels going real fast, and there it goes. Now, of course, this is Science Max Experiments at Large, and we are going to do it again, and we're going to do it much, much bigger. That's why I'm going to the Center for Skills Development and Training.
I thought it was bigger.
Oh, right. Hey, Chris.
Hey, Phil.
How you doing? Chris is from Logix Academy, and he is going to help me max out our dragster. Now, you guys at Logix Academy go into schools and build all kinds of cool stuff with the students, right?
That's absolutely right. This is our dragster over here, actually. And this one has an electric motor, which is kind of fun. And these gears touch.
Ooh.
Wheels get going.
I like that.
And...
Oh, all right. See, our dragster works on good old human power. You pull the string, and there it goes. Now, you have a physics degree, right?
I do.
Which means you know Newton's first law of motion.
Of course, an object at rest tends to stay at rest.
And an object in motion tends to stay in motion. I thought it was gonna come from over there. Yeah, come on. All right, Chris, I want to make a dragster big enough that we can ride.
Whoa, okay. Well, it's gonna have to be pretty big.
Yeah, I think we have enough wood, though, right?
Yeah,
And
looks like
oh, look, I've got some wheels.
Perfect.
These are bike tires, and I filled them full of air, so they're bouncy. Check
Excellent.
it out. Whoa, it's okay.
So, yeah, we build our frame out of wood,
Yeah,
attach the tires on, and then find a way to get them spinning.
and if the tires are spinning,
Yeah.
we don't actually have to push the cart because it'll just go on its own?
That's the idea. The inertia should carry, in the wheels, should carry us down the track.
So in this case, the object in motion is the wheels.
That's right.
And it wants to stay in motion, which means that when it hits the ground, it'll push the cart.
And hopefully us too.
And hopefully us too. All right, let's get building.
Let's do it.
So Chris and I get to work building the dragster. Our maxed out version is gonna look just like the popsicle stick version. A triangular frame with 2 large wheels at the back and a small one at the front. What's more, we're gonna do the same thing to get the wheels spinning. We're gonna attach a rope and give it a pull. When we drop it down, the inertia of the wheels should make the dragster take off.
All right, here we have our dragster. This is nice, Chris.
Yeah, it looks good.
So the only thing I don't understand is what are these for?
Right, so these are gonna help us lift the wheels off the ground like this.
Oh, okay.
Pull it back, and what's gonna happen is we're gonna run real fast with that string, and we're gonna give it a little kick, and hopefully it'll take off.
Ah, all right, I like it. So I just run backwards as fast as I can.
Fast as you can.
All right, here we go. Ready?
Yep, ready.
Okay, safety glasses on. And, oh, wait, did you want to sit on it, or?
Oh, right. Let's wait until we see it working, and then we can...
Okay, dry run.
Okay, dry run.
Ready?
Go! Run, Phil.
And go! Yeah!
So here's what happened. Remember, the cart has no power of its own. It was able to drive away from a stop using the inertia it got from its spinning wheels, and a little bit from Chris's kick.
That worked pretty well.
That was awesome.
Yeah.
I think we can make it go even better.
You think so?
I just think we need a bit more speed.
Yeah. All right, well, let's pull it back to the start.
Okay.
So what, the wheels weren't going fast enough?
Yeah, I think so. I think that you running, was great, but maybe if we use something motorized.
Well, I think using a motor feels like cheating.
No, not on the wheels. Maybe,
Oh, just to get the wheels spinning fast?
Yes, that's right.
But I don't know how that would work.
Well, I was thinking a power drill.
A power drill?
Yeah.
I don't get it.
Okay.
How do we use a drill?
Let me explain. So we'll take a drill.
Right.
And we'll attach it right under this axle here. And that'll get the wheel spinning a lot faster than we had it before.
Oh, I see. So you put the drill right here at the end, and it'll spin the wheel.
That's right.
Huh.
That's the idea anyway. And once we get it up to speed, hopefully a lot faster than before, give it a kick, it should go a lot farther.
Okay, great. So that's way better than me running all the way back with the rope.
I think so.
All right. Now here's the real question. Should we just go for it and have someone ride it when we do it with the drill?
Well, who gets to ride it?
Oh, rock, paper, scissors. Okay.
Let's go.
1, 2, 3. Oh,
yes.
All right. I will get a drill.
Okay.
What kind of bit do we need?
Hex bit.
Here's a fun experiment you can try. If you have something heavy, like this glass of water, and you put it on a piece of paper, you can experiment with inertia. If you move the paper slowly, the glass moves with the paper, because the friction between the paper and the glass is enough to overcome the inertia of the glass. But if you move the paper quickly, the friction is not enough to overcome the inertia, and the glass stays put. And now, let's max it out. Okay, let's do it. All right, now you might be tempted to try this at home, and you can, but please, for me, promise that you'll let an adult know you're about to do this. And don't use breakable plates. Use plastic plates, because this will take a couple times of practicing before you get it right. Put something on the plastic plates, because the heavier they are, the better it will work. All right. Did I mention not to do this at home unless an adult knows you're doing it? I cannot stress that enough. Okay, deal? All right, deal. Here we go. And there you go. Newton's first law. Thank you.
Our dragster worked pretty well, but now we're gonna try sitting on it and seeing if the inertia of the wheels is enough to accelerate the dragster and the human rider. Because we're gonna need a lot more inertia, we're gonna make the wheels spin even faster using a drill.
All right, power tools! Yeah, power tools! Woo! Yeah! Sorry.
When I attach the drill to the wheel, it works really well.
Yeah, that is really gonna work. All right, let's do it for real. So, what do you want? Helmet or blast shield?
Blast shield.
Blast shield. All right, there you go. You ready?
Go. There you go. Whoa, man.
Okay.
Remember, the faster the wheels are spinning, the more inertia they will have.
Ready? Ready. And... Well,
what happened?
So you went a foot. 1 foot. So why didn't that work nearly as well as the last time we did it?
Well, I think my extra weight caused a bit of the problem.
Yeah.
So the inertia wasn't able to carry us forward.
But the whole point of this is so that someone can ride the dragster, because why build it if we can't ride it?
That's exactly right. I think if we're gonna have someone ride it, we need heavier wheels.
Well, on the small one, we use plasticine.
Yeah.
I don't know if that's what we should use.
What if we used car tires?
Car tires? Oh, what, on this?
No, I think we're gonna have to build something bigger.
So so we build a whole new frame.
Yep.
What if we got like the axle of, like the back axle of a car or something?
That's a great idea.
The back axle of a car, and then what, we use the drill?
I don't think the drill's gonna be enough.
To move the, why? You don't think it's gonna be enough to move the back axle of a car?
Yeah, it's too big.
So what do we do?
Well, what's good at moving the back axle of a car?
Well, I mean a car, but we would have to take it off the car, so.
We could use another car.
We could use another, we could use another car.
You could use another car.
You'll have to explain how that works.
Okay.
Let's go get the stuff, and you can tell me how we're gonna use. So how do we use another car to make the first car go?
Okay, I'm thinking we jack one car up,
yeah,
back our big dragster.
Newton's laws in 60 seconds. Isaac Newton was a super genius, and among the many things he did was come up with 3 laws of motion that describe how everything moves or doesn't move. I will demonstrate using myself. Newton's first law: an object at rest tends to stay at rest. An object in motion tends to stay in motion. Newton's third law is for every action, there is an equal and opposite reaction. These sandbags weigh as much as I do. So when I push them forward, I go backward the same distance. Now, Newton's second law is F equals ma. Force equals mass times acceleration. How hard you push something is equal to its mass or its weight times its acceleration, or how much you change its speed. I know, that one's a little bit more complicated, so we're gonna have a whole other segment describing that one coming up. Meantime, let's recap. Newton's first law: object at rest tends to stay at rest, object in motion tends to stay in motion. Newton's third law: for every action there's an equal and opposite reaction. Newton's second, Newton's 3 laws of motion. Now how do I get down? How do I get, oh wait, I know. Oh no, that was not a good idea. That was...
Now it's time for Science So Simple, a caveman could do it. This is a caveman. This is a door. It is a well-known scientific fact that cavemen do not know how to open doors. This is Newton's second law. Force equals mass times acceleration. Our caveman thinks he can open the door if he uses force. Well, what if he was to walk briskly into the door? Then the force that he will hit the door with will be equal to his mass, or how much he weighs, times his acceleration, which will be walking speed to 0. It didn't work, did it? No. Looks like we need more force. If we want to increase the force, we need to increase the mass, increase the acceleration, or both. A rock! That's perfect. If the caveman holds the rock, he has a greater mass. Now we just need to increase the acceleration, which means going faster. Let's try running. Go on. A little further. That's good. Now the caveman is going to run at the door. To get more force, we've increased the mass to a caveman plus a rock. And we've increased the acceleration to go from running speed to 0. And there you have it. That's how Newton's second law works. Join us next time for how doorknobs work.
What?
Our inertia-powered dragster just wasn't maxed out enough. So Chris and I built a second dragster, the Dragster Mark II.
This one is a welded metal frame, and instead of bike tires, we're using car tires because they're much heavier than bike tires. And to get the tires spinning fast enough, we're going to use a car. That's right. We jack up an actual car and have the tires touch each other. Then we can get those heavy tires spinning fast enough to get enough inertia to get me going from nothing. The Science Max build team pulled out all the stops on this one.
Just like the smaller version, the dragster has to be up on jacks so the wheels don't touch the ground as they get spun up. The wheels of the dragster touch the wheels of this working car, which is also jacked up. That's how we're gonna get them spinning fast enough.
Chris is over there. He's got a rope, just like I'm gonna have a rope. And when we're ready, we're going to run forward and pull it off the jacks, and our dragster will go. We hope, right? That's the plan, right?
Yep.
All right.
I think it's gonna work.
I think we should do it. Ready, Chris?
Ready.
You ready, Paul?
Ready.
Fire it up. Go, go, go. Faster, faster, faster.
Keep
Faster,
going.
faster.
Keep going.
All right, Chris. After 3, right? 1, 2, 3, go. Nice. It's pretty good. Yeah, that worked. All right, I think, are we ready for me to be in it?
I think so.
All right, we're gonna do it. The helmet's in the Max van. Do you have the keys for the Max van? Keys for the Max van. Here's another small experiment you can do with inertia. Take a stack of checkers or game pieces like I have here. Oh, or coins. Coins work really well. And a ruler or something else that's flat. This is the kind of stick they give you at the hardware store to stir your paint with. Now you can knock checkers out of the middle of the stack without the stack falling over, if you're very careful. You see, the friction of the checkers leaving the middle of the stack won't be enough to overcome the inertia of the rest of the checkers. Ready? Now, let's max it out. Oh, I have these pizza boxes, and they should work the same way. You see, you get a stack, and don't worry, I've already eaten all the pizza. And I put them on there like that, and now I need a ruler. And what I've got is this cricket bat. You see, it's got a nice flat edge, just like the ruler. Now, if this works right, I can hit it hard enough to knock out just 1 or 2 pizza boxes, and the rest of the stack should stay. Here we go, ready? Science! Awesome. And there you have it. Newton's first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion. An object in motion tends to stay in motion. Usually there's a sign that kind of...
Well, our inertia-powered dragster worked really well. And now it's time for the final step. Me, riding it to glory!
Now, I know it probably doesn't need saying, but don't try this at home. Not that I think you really can try this at home because this is kind of involved, but I figured I should probably tell you guys just in case you were tempted to try it at home. We know what we're doing. We know what we're doing, right, Chris?
Yes.
Yes, yes, we know what we're doing. All right.
Fire it up. Keep it going. Keep it going. All the way. Whoa. All the way. 3, 2, 1, go!
Woo! Yeah! Yeah!
Woo! How's that for inertia?
Wow, look at that. That's amazing.
Cool.
High fives! Yeah!
Let's recap. The weight of the tires, as well as how fast they were going, provided enough inertia to accelerate me and the weight of the dragster. The objects in motion, the wheels, wanted to stay in motion so much they moved the dragster all by themselves. Inertia, and Newton's first law of motion.
Thank you for joining us on Science Max. Let's go again. Your turn?
Yeah, my turn.
Okay. Woo. Inertia! Whoa. Science! Whoa!
Red barbell mark. Action!
I can't do it. Whoa.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Today, I'm maxing out the power of water. Water is very heavy. Pressurizing water to make a water-powered car, water pressure pumpkin carving, water flying, and more. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today we're gonna be looking at water. But water is very heavy, but that's okay because we need it to be heavy for this experiment to work. I don't know if I need that much of it though. Maybe I can get, here we go. Yeah, that's probably all I need. Today, we're going to be building a water-powered car. You'll need a base for your car, like this styrofoam, water bottles, shish kebab skewers, straws, scissors, elastics, paper plates, tape, a square of paper towel, modeling clay, vinegar, baking soda, water, and glue or a hot glue gun if you have an adult to help you, and... yeah, I know, this one is pretty involved. That's why you should go to the website for step-by-step instructions. Take your paper plates and glue 2 together to make a wheel. Then make 3 more. Wrap elastics around your base and then tape straws on the bottom. Trim them down, maybe about that much. Then take your shish kebab skewers and push it through a water bottle cap to make a hole. Then stick one wheel on, put the skewer through the straw, and do the same thing on the other 3 sides. Then take the water bottle cap and get an adult to help you make a perfect hole in it so that it fits your straw. Then use some modeling clay and hot glue to seal the straw and the cap so it's airtight. Attach the water bottle to the base of your car, then fill it with some water and vinegar. Next, you'll want to wrap up a spoonful of baking soda in the square of paper towel so you can make a little package. Finally, stick something underneath the underside of the bottle to raise the end up off the base. Bring your cap and then go outside. Here we are outside. Yeah, I know, we're not really outside, but I have a science lab and you probably don't, so I highly recommend you do this outside. And don't forget your safety glasses. Now, this is why we make a little packet of baking soda, because we want to delay this reaction as long as we can. So I like to hold it there. We'll hold it there with one finger so I can get the cap ready, because we don't want it to react until we can get the cap on, and then kink the straw to keep the pressure inside till we're ready to let it go. Then, at the last second, you want to drop that packet in and quickly cap it, and kink the straw, and woohoo! Woohoo! Haha, there you go, a water-powered car. Now, I know what you're thinking. You're thinking, Phil, wait a minute, that's a vinegar and baking soda-powered car. Well, kind of. The vinegar and baking soda create a gas, and that gas creates pressure in the bottle, and that pressure forces the water out of the bottle. But it's the water leaving the bottle that creates the thrust. The water going that way pushes the car that way. Newton's third law, every action has an equal and opposite reaction. So what we're gonna do is max out the water-powered car. Figure out how to get water going that way so we can go that way. But we means me and someone else. Who can help me? Oh, I know, Anthony from the Ontario Science Centre. He'd be great at this. Hopefully he's not busy. We're gonna max out the water-powered car. Ha. Anthony! Phil, sorry about that. Did I scare you?
Don't worry about it.
How you doing?
Awesome, thanks.
Great. I was wondering if I could get your help on an experiment.
Yeah, okay. Which one?
I'm building a water-powered car. It's gonna be great. It's Science Max headquarters. I'll show you.
Phil?
Anthony, I'm here.
Whoa. Phil, where are we?
Oh, this is the parking lot for Science Max headquarters. So,
Okay.
today, I want to max out the water car.
This thing is awesome.
Yeah, so what you do is you use vinegar and baking soda,
Yeah.
and you pressurize this container. And,
Okay.
And the water shoots out that way. So the car goes this way.
Ah, Newton's third law. Every action has an equal and opposite reaction.
Yeah, you know your
Okay.
stuff. This
Okay.
is why you're here. This is because I could really use your help and advice on how to make this bigger.
Okay, so we're gonna need a bigger tank to pressurize. So this, what about something like this?
So we need something that can hold pressure. Do you think this would work?
I don't know if we'd wanna...
And we'd have to put like pressure fittings on the barrel, like cut a hole
Yeah.
and weld them on. I don't know if that's...
Something tells me this wouldn't work. So we
Okay,
need,
sure. I got some other stuff over there maybe that we could
Check this out. Yeah, I think this would work. This would work a lot better.
use. Well, this is my stand-up wash tub base.
Your what?
So
Yeah.
we'll reuse it. Yeah?
Okay, you know what I'm thinking
Yeah.
now, though? I know
Yeah.
this... The problem is, I think this is like an oil drum, right?
It is.
And,
It's an oil tank from a house.
and these things are not built for pressure.
You can get water tanks that you pressurize.
Like hot water heaters, yeah, you can pressurize. They're built for that stuff. You pressurize them in your basement, and then the water travels up to like
the top
your
floor.
shower
That
or
makes
something like that.
So all we need to do is get a pressurized water tank,
Okay.
put water in it, put pressure in it, and put it on wheels. And then we open the valve and it goes, right?
That sounds amazing.
All
Yeah,
right.
let's get to it, man. Okay. we
I got
need,
some water tanks over here in this corner of the parking lot.
Seriously?
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. When you're a professional chef like me, you spend lots of time perfecting the perfect recipes. I know my way around a kitchen, and today I'd like to show you one... That's not the fridge. Oh. Today I'd like to show you one of my favorites. Quail truffle gazpacho cakes on a plate of ice. Beautiful. And here's how to make it. Take some quail, some truffle, and some gazpacho and put it into a cake. Delicious. And here's the interesting part. How to make the plate of ice. Ooh, how did I do it? Well, I tried many different methods, and none were very successful. But now I let science do the work for me. So here's what I do. You see, I've got my large block of ice, and I've got a fishing line over the top, and on the bottom, I've got 2 heavy weights. Now we wait.
The heavy weights put pressure on the fishing line. This pressure melts the ice where it's pressing down. As the ice melts, the fishing line moves through the block of ice and eventually cuts its way through.
There we are. My hours of waiting have almost paid off. You see, I've got a perfect line through the ice, and I stopped it just before it finished. It's the pressure of the line on the ice that makes it work. The same thing happens when you use ice skates. You see, it's a very thin line, and your body weight presses down on the ice, melts it a bit, and that allows you to glide across the ice. It also allows me to just pop this off. There you are, you see? Perfect plate of ice to put my delicacy on. Let's just try that now. There we go. So I've joined Anthony, and we're going to max out our water-powered car. Our small design works by creating gas, which creates pressure, which forces the water out of the bottle, creating thrust. Our new plan is to get a water tank, put it on wheels, and put water in it. Then we use an air compressor to pressurize the air inside. When we open the valve, the water is forced out this way, which causes our water car to go that way. Okay. Ha-ha! So, water car, maxed out version.
Huge.
Water tank.
And filled with lots of water and lots of air. Too. Yeah, pretty good, right?
Whoa.
It's a lot of it. So,
Did it mess up my hair?
No, you look fine. You look great.
Okay, good.
Now, the only thing left is we just gotta open this valve here, right?
Yeah. You want to do the honors?
Yeah, let's do it. Okay.
Okay, here we go. 3, 2, 1, go! We open the valve and our pressurized tank moves forward. The air pressure in the tank forces the water out with enough force to move the tank.
Awesome! That was awesome!
That was a great run, yeah.
That's amazing.
So pressurized water tank on wheels.
Totally worked.
Totally works.
Total success, yeah.
So, because this is Science Max, the only thing we can do now is make it bigger.
Bigger,
right?
exactly,
Okay.
yeah.
So, problem is,
I don't think we're gonna find a tank bigger than this one.
Yeah.
So.
because then it would be too heavy, right?
Exactly,
Much
way too
bigger.
heavy. Maybe what we can do is just get a lot more water,
Okay.
and then we find a way to pressurize the water.
Oh, so don't pressurize the whole tank, just the stream of water that's going out
As
of
it
the tank.
comes out, exactly. Something kind of like a fire hose.
A fire hose, right.
So
we take a big container of water.
Right.
And I guess we would need a pump.
Yeah, like a pump would be perfect.
So then we suck the water out of the container, put it through the pump to pressurize it, shoot it out of a fire hose.
And then our car goes flying.
Goes flying.
Okay.
Yeah, let's do it.
Yeah. All right, amazing.
When water is going fast, it has a lot of force. This is a power washer. It's made for cleaning concrete and wooden decks, but it doesn't use soap and it doesn't use heat. It only uses the power of water. Let's try it out.
The power washer creates a stream of water that is moving really fast. It has the force to clean concrete, strip the paint, or even the Science Max logo off wood. But how do I max out the power washer? What's the most ultimate use I can think of?
Power washer pumpkin carving.
The power of the pressure washer creates a stream of water strong enough to make short work of my pumpkin. Power washers may only shoot water, but they can be dangerous, so don't try this at home.
Yeah, science!
The Wizard Academy. All you have to do is demonstrate true magic, and you'll be granted entry.
Send in the next candidate. Oh, no, not Overwhelmo.
Did
someone say Overwhelmo? No, wait, no. Next. Oh, not that. Okay, good. Okay. Behold, it is I, Overwhelmo! Welcome back, Overwhelmo. If you can truly demonstrate magic, you may join the Wizard Academy. A glass of water! No, wait, that is not the whole trick. Okay, hold on. Okay, and this, a waterproof playing card. I put the card on the glass and flip it upside down, and then I say the magic word. The magic word. And behold, magic! Yes? Is that it? Yes? Well, it's not magic. It is defying gravity! Nope. The water would fall and the card would fall to the floor. It's not magic. This is magic! No, it's science. Horse feathers! Look. The reason the water doesn't come out is the air at the top of the glass keeps it held in by suction. More air would have to get into this glass to decrease the suction, and because the playing card is keeping a seal on the glass, the suction of the air is holding the weight of the water up. Balderdash! All right, look, let's do a little experiment then, shall we? Let's move the playing card just a little bit from the edge of the glass. You see those bubbles? Yes. That's bad news. Science, not
Magic.
Well, I will return, and then you will see your mind will be melted by the. No, that's not my music. Hold. You will rue the day when. That's not my. Hold. Overwhelmo shall return.
Our maxed out water car worked pretty well. Now it's time for something even more maxed out. We start with a giant tank on wheels, we add a pump to pressurize the water, and a fire hose to shoot it out the back. What's more, this version is big enough for me and Anthony to ride.
Water car!
Amazing! Is the more super improved water car. This tank holds 1,000 liters, and right now it has 720 liters of water.
We have a pump. That's right, our water pump. So the idea is we take the water from this container out through your hose, really pressurized, going really fast that way. Our car goes really fast this way.
All we gotta do is just turn on the pump and we're ready to go. So we fire up the pump and the water stream comes out really strong. So strong I can barely hold on to it.
Here we go!
But even so, there's a problem.
What's going on back there? I got it! Yeah. Nothing happened. No, nothing really. Well, something happened. We got wet, but it didn't really.
It's too heavy.
Too heavy.
So you're on it and I'm on it. That's a lot of weight. We don't ride it. That's something.
Yeah.
Also, this is kind of going crazy.
Yeah, because if nobody's holding it, it's just gonna flap around.
So we'll have a brace here.
Yeah.
Shoots it that way. That's good.
And then we'll need. I feel like we'll need something to kind of propel it. Maybe a better propulsion system. Kind of like one of those steamboats.
So we put a big paddle wheel here.
Exactly.
And we aim it. I guess we aim it down
at the. Yeah, exactly.
Like that.
And then
at the paddle wheel, and then the paddle wheel spins, and that propels the car.
Exactly.
Right?
Right.
Okay.
Okay, well,
we can do that. Let's do it.
Sounds good,
We'll
yeah.
put it together. You know what? I have a paddle wheel because I had a failed hydroelectric.
This is called flyboarding. Whoa. Whoa. Powerful jets of water are being shot out from this board at my feet. Whoa.
The engine on the watercraft behind me creates the water pressure, which travels up the hose and through the jets. The force of the water is strong enough that I can use it to fly around. So what's the difference between this and a water car? Well,
We don't have to take that much water with us because it starts in the lake and ends up in the lake. So the only water I have to carry is in the hose that goes up to the platform.
flyboarding is lots of fun, but it takes some practice to get it right. Balancing on jets of water isn't easy, but I got the hang of it.
It's all due to Newton's third law. For every action, there's an equal and opposite reaction. Physics! Woohoo!
Our maxed out water car didn't work so well. The main reason is that that much water is heavy, 720 kilograms.
Yeah.
So Anthony and I have a plan. Rather than rely on the force of the water going straight out the hose, we're gonna put a water wheel on the back of the water car. A water wheel works by catching water in the segments of the wheel. The weight of the water on one side of the wheel causes it to start turning. But we're gonna use the weight of the water and the pressure of the water. Hopefully, both combined will be enough force to turn the wheel, which will drive our water car forward. A little construction, and we have it ready to go. Okay, so here's the latest version of the water car, water wheel!
Yeah.
All right.
Yeah, there we go.
We try it out, but there's a problem. The trick with the water car is the water itself weighs a lot. Every liter is 1 kilogram, so our 720 liters we start with is way too heavy to get the car moving in the beginning. But as the water gets pumped out, there's a sweet spot where the weight is low enough the water car might move. But then there's only a little water left, so it's a balancing act. We fill it again and see if we can come up with a plan. Okay, new and improved version, only half full. So the idea this time is because we're starting with it only half full, right?
Yeah.
Then it'll begin to go a little easier because it won't have as much weight as it had the last time we did it.
And Phil,
Yeah?
I can't even move this thing.
What?
I think there's too much fuel. There's too much. Yeah, there's no way we can move this. There's no way this is gonna be able to.
Even half full, you
Even
can't
half full.
move
I
it.
think we need less fuel than we gotta get down to like maybe like a quarter or something like that.
The thing is, we ran it from the full tank last time, and it never
So
moved at all.
What if we gave it like a push to kind of help it get over that little bump of energy?
Ah, so give it the first push when it's still got a bunch of water in it. We give it a bit of a push, and then maybe it'll go on its own.
Exactly.
Okay.
Wanna
Yeah.
go?
Absolutely. Let's do it. We start the pump and wait for the amount of water to get to just the right spot. Then we give it a push while it's still kind of heavy to start it moving. Sure enough, that push makes all the difference. The water car is light enough to roll, has some momentum to keep it going, and the force of the water coming out the pump is enough to keep it moving forward on its own.
Still going!
All right!
Amazing! Yeah! Look at it, man! This thing worked like a beauty!
It worked all, it went all the way.
Yeah!
Way to go. The water car, finally, a success. It was the push.
It was the push. That's all we needed to get it going.
A bit of a push to get it going and a lot less water, and there you go. It totally works. All right, you want to do it again?
Absolutely!
All right, here we go.
Okay.
See you next time on Science Max Experiments at Large.
So much easier to push it without any water inside it.
Ah! Let it go and...
There we go. Oh, careful.
I can't really see with my goggles.
Behold the power of physics! Yeah.
The door's full.
This is called foot. Whoa! All we have to do is wait. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Gravity, gravity, gravity. Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity. You win this one, Gravity. From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max, Experiments at Large, we're going to use everything in the power of science to defy gravity. Ha! We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh,
Maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it to make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. We're gonna, oh yeah, I gotta clean that up. We are going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I came
Are you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
it's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To replace the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa!
Gravity defy. Gravity defy. Gravity.
Look at it fly! Defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why. When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it. Until there's no more tension, and then the top passes the bottom and the whole thing. That is how it works. But here is the real question. Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring! Let's max it out! Bring it. Don't tangle it. So, now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go! A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it. So there you go, an almost gravity-defying spring!
Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa.
Sonia and I are maxing out the hoop glider out of bigger and better materials.
This is the largest tube I have, right?
A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and...
Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited.
we take our plastic and metal hoop glider outside to test it and...
Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it?
Sonia and I made a very solid design, but the problem with it became pretty obvious.
Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down. So you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon and it had a, there. A giant balloon. And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Towards the center of the Earth. Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes, gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off. back to our hoop glider, which was too heavy. Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground. I see.
so we need something that's light.
Light.
And something that's strong.
And strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out. Hoop glider dance! Okay, 3, 2, 1.
That's pretty good!
That was amazing! Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good!
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it. Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version.
This time I used cardboard.
And I made this! Made a slightly heavier one.
Let's do it.
Okay, 3, 2, 1, go! Not bad. My turn.
Here we go.
Okay. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome!
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But I think that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. And the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do. But the question is,
how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well.
That was
Pretty
amazing.
good. Here we go.
But we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
A giant slingshot!
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great! So there you go. Giant hoop glider. Yeah! Science Max. Experiments at large. Nicely done.
Nice.
What more can you ask for?
Well, my turn.
Hey, see you next time.
I'm the marker.
Take 8. My goodness.
I play the wobble.
Wobble.
The wobble.
Forgot my line. Forgot my line. Going back down.
Wobble, 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 wobble.
Hello? Hello? Hoop glider central calling. Yes? You were having problems with your hoop glider? Oh, what's wrong with it? Oh, you're using it as a phone? Yes, well, that's your first mistake, yeah. Today on Science Max, I forgot to tell you my name. My name is, I'll do it.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max!
Newton's third law is the science behind balloon-powered rocket cars. It's also the science behind a maxed-out rocket car that I can ride. Plus bowling balls and an interrupting sign. Today on Science Max, experiments at large.
Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster, and then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle, or whatever you're going to use, and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxidrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right!
And last but not least, the Regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out, because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built, and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training, and we're gonna use the science behind this small balloon-powered car, and we're gonna make it big. That science is Newton's third law, but there's plenty of there's plenty of time for this later. We're not doing this bit now. We're doing that bit in a minute, so we could. No, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're going to be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right. So how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah.
You got it?
Yeah. Okay, let it go.
Okay, go.
Let it go.
I did.
You did let it go.
I just let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay, balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can... All right, so I don't know if that's safe to do that, so we'd have to build like a cage or something?
Yeah, I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
Get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tank, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time. Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why.
Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity, he gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be Science Maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out. Now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back. When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction. Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, huh? Oh, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use a compressed gas cylinder, just like a balloon,
These cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right. So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked!
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're going to go faster forward. Newton's third law.
Newton's third law. High five. All right, let's do it.
All right.
Whoa. Okay.